This presentation is about one of the most famous structural engineering failures in history, the Tacoma Narrows Bridge collapse of 1940, known as Galloping Gertie. This bridge fundamentally reshaped how engineers think about aerodynamics, stability, and structural safety. Today we will look at what happened, why it happened, and the lasting lessons it left behind. The Tacoma Narrows Bridge was located in Washington state, spanning the Tacoma Narrows Strait of Puget Sound. It officially opened on July 1st, 1940, and tragically collapsed just 4 months later on November 7. At the time, its main span of about 2,800 feet made it the third longest suspension bridge in the world. Despite the promising start, the bridge became infamous as one of the shortest-lived major engineering projects. The bridge was designed by Leon Mosaiev as a very slender suspension bridge. It had a deck width of only 39 feet and an unusually low depth-to-span ratio of 1 to 350. To save money, stiffening trusses were kept to a minimum, which made the structure more flexible. The focus was on elegance and economy, but this came at the cost of stability. Even before the collapse, problems were evident. The bridge was notorious for its vertical oscillations, so much so that motorists said it felt like riding a roller coaster. Engineers attempted fixes with tie-down cables and hydraulic dampers, but nothing worked. Because of its constant rhythmic motion, locals gave it the nickname Galloping Gertie. On the morning of November 7, winds of around 40 miles per hour swept across the bridge. This wasn't an extreme storm, just moderate wind conditions. But suddenly, the oscillations changed from vertical bouncing to violent twisting, with the two halves of the deck rotating in opposite directions. The bridge deck finally tore apart and collapsed into Puget Sound. Thankfully, no human lives were lost, though one dog perished. The entire collapse was captured on film, and it remains one of the most iconic engineering failure videos of all time. The image on this slide shows how the Tacoma Narrows Bridge collapsed due to aerodynamic instability. Unlike ordinary bridge designs, where wind could pass freely through trusses, the Tacoma Narrows use solid girders that force the wind to flow around the deck. This design choice made the bridge highly sensitive to wind. As the wind moved past the bridge, it created alternating swirls of air called a Kármán vortex stirred. These vortices produce periodic forces that pushed and pulled on the bridge deck. At, at first, the deck oscillated in gentle wave-like motion, but as the wind energy matched the bridge's natural frequency, the oscillations quickly grew stronger in a process called aeroelastic flutter. The motion then shifted from simple vertical movement to violent twisting or torsional loping as shown in the lower diagrams. The twisting stressed the suspension cables, and as the flutter intensified, several cables snapped. Eventually, the oscillations became uncontrollable, and within minutes, the central span of the bridge tore apart and collapsed into Puget Sound. So, what actually caused the failure? It wasn't classic resonance, as often misunderstood. The real cause was aeroelastic flutter, a self-exciting vibration where the wind itself feeds energy into the structure. The torsional mode of the bridge was triggered, and because the design lacked adequate aerodynamic stability and torsional damping, the twisting amplified until failure. Contributing factors included an underestimation of aerodynamics in long-span bridges, overconfidence in simplified calculations, and inadequate wind effect testing. The Tacoma Narrows collapse completely changed engineering practice. First, wind tunnel testing became essential for long-span bridges. Engineers also recognized that torsional stability must be carefully analyzed. Collaboration between structural engineering and aerodynamics became critical. Finally, it underscored the importance of engineering ethics, the responsibility to design not only for strength but for safety under dynamic conditions. In short, this was the birth of modern bridge aerodynamics. A replacement Tacoma Narrows Bridge opened in 1950, built with a much more robust and aerodynamically stable design. Today, the original collapse is a standard case study in civil engineering and physics courses around the world. It stands as a powerful reminder that dynamic forces can be more dangerous than static loads in slender, flexible structures. In the next case study, we will turn to the Quebec Bridge collapse of 1907 in Canada. Unlike the Tacoma Narrows, this failure wasn't due to aerodynamics but to static loading miscalculations and material failure. It highlights the importance of peer review, redundancy, and humility in design. Another key turning point in the history of structural engineering.